Hello, I'm David. I'm the coordinator of the Maths Learning Centre. It's a revision seminar for multivariable and complex calculus. It's semester 1, 2019, and I've been asked to talk about integrals. So, nice seat down the front here. Yeah. I would normally show my face at this point, but the cameras are very carefully set up in certain ways, so I don't want to move them. I'm sure it will appear at some point. But it's just for the people who are watching it in the future to know what I look like, but that'll happen. I've been specifically asked to talk about integrals in this course, and what I'm going to do first is I'm going to talk about all 9 integrals in this course and organize them so that we can see how they're related to each other. So that's where I'm going to start. But before I get to that, it's probably important to just tell you how I think about functions so that some of the things I say will make sense. So, right. When we learned about functions first, we learned about them as a graph. And there were all these x's, and you put the x's in and each of them produced a y. And then if you collected together all of those dots, you would get something. And that's how we learned about functions to begin with. This is the graph of a function that is most of the time not a useful way to think about functions in multivariable calculus. We actually have to go back a little further from that to think about functions in multivariable calculus as just having an x-axis, and every value of x has a number attached to it. Or possibly something else, but for the moment a number. And this one maybe has a number 4, 6, 3, something like that. And each number on the x-axis has a number attached to it, and that number is the function value. Okay? And as we move along here, if we moved along here from, say, well, and the ones in between have their own function values. Maybe this one is 3.5 in the middle, whatever. As we moved along this x-axis from one place to another, we could collect up all the numbers that we see and get some sort of total, and that's what an integral is. And sometimes the numbers will be negative, and so the total will go down as you move along, and sometimes the numbers are positive, and then the total goes up as you move along. And it'll be different if you're moving forwards or backwards, because you want to take that into account. We're going to want a whole extra table. Okay. The reason why this is so important is that if I have a function that doesn't take points on a line but takes points elsewhere and produces numbers, I'm not necessarily going to be able to draw a graph of it. So, for example, if I drew a graph on the xy plane, this tape is awful. I'll just use this. If I drew a graph on the xy plane, like an x-axis and a y-axis, this way for the purposes of the video, then every point in this space here would have a function value. And maybe, I'm just going to write them down where you can't see. That'll do. It's enough for now. Every point has attached to it a function value, so maybe each of them has a function value spread out. Every point, technically every one of them has a function value, but oh, I needed one more. Okay, and so the function value is there whether you calculate it or not. And I can't necessarily see it. I might need to open this window and notice that it's 5 at this point. And this one is 7. You can't see it from there, but I can. 8. So I think of a function as an advent calendar. So one of those little things with the windows that you count down to Christmas and it's got chocolates in it. And the chocolate is there whether you open the window or not. And when you open it, you see what it is, and you go, oh, look, it's a candle. Yay, I can eat it. And that's how I think of function in 2D. And in 3D as well, it's just that there's ones up here too. Oh, this place, I'll just open the little window. Oh, it's 17. Okay, cool. And this point has one. Oh, it's -7. And every point in space, you can figure out what number goes with it. And you can collect together... I don't have anything big enough. Sure, this will do. You can collect together something in space like this and go, I'm going to try and collect together all the numbers that are on that, attached to the points on that surface. And that would be doing an integral. That's what I'm thinking. So just so you know what's in my head, that's what's in my head when I'm thinking about these things. Right. And it was all worth it just to do that. Okay. So, an integral is I lost my pencil. Is a collecting together of all of these numbers, taking into account how much space has the same number. So, if I had a zone here that were all 6s, the 6s would count for more than a teeny tiny zone that was 4s. And so what I do is I imagine it very, very small. Zoom in with my magnifying glass. And within that, there's all these little marks. And the idea is that even though it goes from 4 to 6 on this zone, if I go a very small amount of distance, it's not going to change very much. And so I'm going to say that the amount that I accumulate a number like this here, they're almost going to be all 5.15 in this zone here. And so I'm going to say that I have 5.15 times this width, and that's how I'm going to add up all of the answers. Okay, cool. Right, I can get on to what I was planning to say actually now. So, there are 9 integrals in this course. Technically a couple of extra ones on top of that, but about 9. And they each occur in different dimensional space, and some of them are based on different kinds of functions, and they're integrating across different kinds of objects. So there's 3 things that will distinguish the different kinds of integrals you have: which space you're in, what object you're integrating across, and what kind of function you're integrating. And they produce 9 different options. Okay, so I'm going to start in one-dimensional space. This is not technically in this course, but you keep using it, so this is where it is. So in 1 dimensions, you just have like an x-axis, and every point has a function value. Whoa, what happened then? Every point has a function value, and we do an integral the way we normally do an integral, where we go, well, the integral of f of x dx from one place to another. There's a and there's a and there's b. Is what I get when I accumulate all of these things, these function values in here. Now, if I'm good, I can go back to the way I used to imagine functions and go, well, each of these function values is interpreted as a height, and I can think of it as an area if I want. There's no screen there. I'm used to having 2 screens. I can think of it as an area if I want. And what we learned from the fundamental theorem of calculus was that if my f happened to be the derivative of something already, then I could do this. And you've been doing integrals like that for a while. We did them all through Maths 1. We spent lots of time figuring out how to do integrals of very crazy and difficult functions in Maths 1a. And then we use those integrals to do differential equations and blah, blah, blah. We've been doing integrals like that for a while. And this here, this bit here, is the fundamental theorem of calculus. It tells you that if your function is already the derivative of something, then I can do the integral by just finding out what the thing that it's the derivative of is at the two endpoints and subtracting them. Okay. Right. That's one-dimensional. And we're good in inverted commas at those relative to the new ones we've done. And I'm just going to put this on my table over here, and we'll come back to it in a second. So that's in one dimension. It's all good. We're good at those. In 2D, there are three integrals. And there are two that go with functions that produce numbers at every point. So we're going to have, okay, f of, now my x is a point in 2D as opposed to just a single number. And it's going to produce a real number. And this is called a scalar function, I believe. Scalar field, maybe. Nope, okay. Okay, so that's the kind of function we have. This is the one that I drew a graph of before. Every point has a number attached to it. And I'm going to make this as similar as possible to the 1D case, which is where there was a curve, and I wanted to add up all of the numbers that are produced on the points along this curve. So this curve I shall call C. Is that what your lecturer calls curves in this course? Not gamma? Oh, sad. It's fun using Greek letters. So what I'm going to do is I'm going to do an integral like that. And the idea is that this is the number that the point x produces. That's my point x on the curve. And this ds is a very small movement along the curve. And if it's small enough, all of the function values on that zone will be the same, roughly. And so I can do f of x times that function, that width, and add them all up like that. Okay. So the first thing I need to say before I do anything else is that you can only integrate a number. There is no such thing, technically, as integrating a vector. We have to turn it into a number in order to integrate it. So what we have is we have a number here multiplied by a distance, and we add up all of those, and we get a total answer. Okay, this is all well and good. You could, if you had the function value at every point, you could totally approximate this, and you could flatten out, just a second. You could take your curve and flatten it out. Sorry about that. Let me try that again. You could take your curve and flatten it out and go, aha, each of those points. So this was this point and it had a function value, and maybe it's this. This was this point and it had a function value, maybe it was this. And you could collect together all of those and do that integral. So flattening out the curve into a straight line and do the integral that we used to do in one dimension. For the purposes of scanning this later, I'm not going to be able to I was going to sticky tape the string on, but it's not going to work in the scanner, so I'll just draw a line. Cool. All right, and that's how we do it. And so what we're going to need to do is be able to have some variable that keeps track of where I'm up to on this line, like where I'm up to on this line. And that's called parameterization. That there is a function that goes from here to there. traditionally called t, because we imagine that the point is moving and the t is time. That's why we use t. Also, it's just the next available letter that hasn't been used yet. You know, we've got x's and y's and z's, and u is for substitution and v is for velocity, and there's not many left. Okay, so what I've done here is that this t is a literal length along the curve, but it doesn't have to be. This line here does not have to be the same length as this. It could be that it could be half as long. It could be that zones here move at different speeds on this curve. So it could be at the beginning it's moving really fast, and then at the end it's going really, 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 really slow. And it'll be moving at different speeds. And so what you're actually going to have to do this sum here, is keep track of how fast the curve is moving as t moves forwards. And take that into account when you do your integral. So this parameterization doesn't usually have a name, does it? No, that's all right. The actual x that we're going to use is going to be based on the t that we have. It's now a function of t. And so what we're going to do is we're going to think that a little change in s okay. Just a second. See this ds here? It's an arrow. It's an actual vector. And this ds is the length of that. So what we're going to have to think is that a vector movement along the line is going to be some multiple of the movement of t here. T moves a bit here. That'll cause us to move a little bit in space on the plane here. So this moves forward, that moves forward. At this point, this moves forward, maybe that moves forward a lot. At this point, this moves forward a little bit, maybe that moves forward a little bit. And it produces a vector. And when we do derivatives, a change in the output is the derivative multiple of a change in the input. That's how all derivatives work. And that will keep track of how t moving causes the point to move. And this is that. Does your lecturer write this as r? Whatever, sorry. I find it really hard to call it r. It's a position in space, so I want it to be x, but that's all right. So that's what this is, and ds is the length of that. Does your lecturer use double lines for length? Okay. So it's the length of this. dt is just a number, so it's going to come out anyway. So we've got technically this. Like that. Yeah. And so actually my integral becomes t going from a to b of f of x of t times dt. I'll do some examples, but I want to just talk about them all first, if that's okay. So different parameterizations will cause you to create different formulas at this spot, but when you sub in the endpoints and subtract, you will get the same answer. That's the idea. So if you have two different ways of parameterizing the curve, they should produce the same answer ultimately, because whatever changes are made here by subbing in x of t into f are cancelled out by multiplying by this. And are cancelled out by using different numbers at the two ends. Okay. So this is the first integral I'm doing here. Okay. So there are lots of things happening here to keep track of what was going on. There were parameterizations of curves. The only way for us to turn this integral into the integral that we're familiar with is to somehow keep track of where I'm up to on that curve, and that's what a parameterization is for. It tells you what every point on the curve is. And the only way to keep track of how changes in this t causes changes in the function is to keep track of how it changes what the x is, which is what this bit here is. Okay. Any thoughts at the moment before I move on? or questions? All right. Cool. So I'm going to keep going with my scalar function. Okay. So now, instead of doing a curve, I might do an area. I think it's R for region in this course. Does that sound right? Yeah. I'm just going to write curve and path on here just to make sure I've got it right. Okay. So we're going to do a region or an area. And what we're going to do is we're going to add up all of the function values in every point in this area, taking into account how much space they're taking up. Just push. Yep. Space over is table. Taking into account the space that those take up. And so if it tends to be close to 6 for a while, then the 6 will count more. So I want to count each number for the area that it's sort of contained in. And so we're going to do this. It's called a double integral across the region of f of x dA, I believe, is a traditional way of doing it. And this dA means a very small, tiny piece of area. So I have two ways of, well, I'm going to have to, just the same as I did with my curve, I'm going to have to find a way of keeping track of where I am inside this region so that I can keep track of adding up all the little bits. And so I need to find ways of doing that. And that's technically a parameterization of the region. So I need to figure out, based on two numbers, where I am in here. So that's what I'm going to need to do. So I could do this if I wanted. So just a second, I'm not going to do that. So this curve is not too bad. I could say, well, the x has to go from here to here. And once I've chosen an x, the y has to go between that top function and that bottom function, like here. So for each x, I get a different choice of what y's I can use, and then that will locate where I am inside this curve. So inside this region. So maybe this is this. And then I could say, well, choose x between a and b, and then choose y between, well, different top and bottom, between the bottom and the top, and these change depending on which x I'm up to. That's normally how I would go about locating something here. So when I look in my magnifying glass, there is a point here. It's got an x coordinate and a y coordinate, and there's a little area around it. And that area is my dA. And it also has a function value. I can open my little advent calendar window, and there's a function value there. I'll multiply the function value by the area that I'm at and add them all up, and that will be this area here. So this will tend to turn into, you know, x between a and b, y between some function of x and some other function of x, like that. Because what we're imagining is that the dA is dy times dx. Okay. Problem is, well, not problem, just a different thing. If your coordinates are not running by a dy times tx sort of thing, sorry, it should be or dx dy, it doesn't really matter. It does matter, though, that you need to have that the first one that happened has to be the last symbol. So if this is about x's, this one has to be about x's as well. And then the next one in both have to be about the same variable. They need to be in the wrapping in like brackets. Okay, so what can happen is that you might not like your coordinates to be in terms of x and y. If you're extremely lucky, you may be able to locate a point in this region instead of by x and y coordinates, by some other parameters. In the same way that I can use some letter t to say where I am up to on my curve, I could use some other letters, s and t or theta and r or whatever, to locate where I am in here, and that will be a problem because the dA is a rectangle and changes in curvy things are not going to be rectangles. And so I need to find a way of converting, and I don't have room for that on this picture right here. But I think I'm going to just mention it here and we'll do an example later. So we might have, so that's one way. The other way might be to have a parameterization, in which case you have like an r and a theta, and together they produce this point, something like that. So if you have a parameterization, you're going to have to say, when you have your parameterization, that dA is going to be, now what does your lecturer call this? J? I hope they call it J, like a Jacobian. Anyway, it's a thing times dx times the dr d theta. And this thing will be a derivative that tells you how dy and dx change when dr and d theta change. So I think it's like dr theta on, no, dxy on dr theta, something like that. So in the same way that when we moved this t, we had to figure out how position on the curve changed when t moved. If I move these r's and thetas, I need to see how the area changes when the dr and the theta move. So I'm going to need to find a way of doing that, and it's some sort of derivative. Okay. So there is one more 2D integral, which you may not recognize as what I'm about to call it. Maybe you have something that instead of producing a number every time you do it, produces a vector. So what if they've all got an advent calendar window, but when I open my advent calendar window, it produces a vector instead of a number. And every one of these, maybe they all have a little arrow in various different directions at every one of these points. And it's not really here, it's inside the advent calendar window. You have to open the window to see it. It doesn't really live in R2. It's sort of attached to this point somehow. So if I wanted to represent that, normally you draw little arrows at every point. But for me, these Cuisenaire rods. So maybe at this point, the vector's pointing, that's black. The vector's pointing this way, and maybe at this point, the vector's pointing that way, and it's that long. And maybe at this point, the vector's pointing that way, and it's this long. And every point has a vector attached to it. It's attached at its end point. And maybe some of them, there is no vector, and it's just like a point, just 0. And every point has a vector. And I may be able to trace a curve where like that, and try and figure out what to do with all the vectors that live at all the points on this curve. So this point maybe has a vector, and this point might have a vector that's a bit bigger, and this point has a vector, and this point has a vector, and all the points have vectors, and somehow I have to figure out some way of combining these vectors together as I trace the curve. That's what I'm going to have to do somehow if I want to do an integral of a vector function along a curve. What am I going to do? I have to turn my vectors into numbers. I can't do integrals of vectors. I can only do integrals of numbers. So what I'm going to do is I'm going to figure out how much of each vector, what this piece of each vector is pointing in the same direction the curve is going. So this point one, the curve's going this way here. So the amount that's going in the same direction of the curve is here. And I'm going to take that number. That's going to be my number. This one, the curve is going that way. There's hardly any of this vector in the same direction of the curve. This one's pretty much perpendicular to the curve. There's hardly any. Each of these vectors can be replaced with the length of the component of that vector that's in the same direction the curve is currently going. That's what we're going to do. I lost my pencil again. All right. Okay. So we have our curve, and at every point on the curve, at technically every point in space, there's a vector. Every point in the plane, there's a vector. And some of those are attached to points on the curve. Okay? And for every one of them, I'm going to do this. So here's my magnifying glass. What I'm going to do is I'm going to say, well, the curve is currently going this way. That's the tangent to the curve here. And I'm going to figure out what component of this is in the same direction the curve is going. And that number, that's what I'm going to add up at every point. So now every point on the curve gets a number, which is the component of the vector field that's in the same direction of the curve. And I'm going to add up those numbers. Right, and sometimes they're positive, and sometimes they're negative, and sometimes they're 0. So I'm going to make the F bold as well, because it comes out to be a vector answer. So to figure out the component of something that's in the same direction as something else, that's what dot products are for. We did it in Maths 1B when we did orthogonal projection. We went, all right, how much of this vector is in the same direction as this space? I'll dot product with the basis of the space, and that will give me the coefficient. So this is saying component of f of x in the direction of ds. Pretty much, something like that. And we want to add all of them up. But that's okay, because we know what ds is. As long as we've got a parameterization for our curve, we can do it. So we had our t, and our t produced our curve. So as long as we can do it, we can do this. We know that ds is actually the derivative of x dt. And this is a vector. It's the direction, that's this vector here. And so therefore, this is t goes from a to b of f of x of t dot x dashed of t dt. And this thing here will come out to be a number because it's a dot product and we can do the integral. Okay. So what did we have here? We had a vector function along a curve. Right. Well, let's just organise what we've got so far. Okay. So in one dimension, there's only one kind of function and there's only one kind of integral. You know, vectors in R1 are just numbers. And then in 2D, we had, put that there. In 2D, we had curves. We could do an integral of a scalar function across a curve. And we could also do a scalar function across an area. So these are both scalar functions. And we can also do a vector function across a curve. You'll notice there's a hole here. Vector functions across areas is stupidness in 2D. Doesn't make any sense. And we'll get to why in a minute. But this is what we have here. So my scalar functions can be integrated across curves and regions, and my vector functions can only be integrated across curves in 2D. And this is what we have so far. And you'll notice that these two were both done by turning it into this. We turned this one into an ordinary integral by taking the length of a vector to turn it into a number. And in this one, we turned this integral into an ordinary integral by doing a dot product in order to produce a number. This one is a little different, actually. We turned it into a nested integral. At each level of x, there's an integral to tell you a number, and then we integrate that number answer from the integral to get the total integral. So it doesn't really go directly here. Okay. So there's our differences. It's always good to try and see similarities and differences. So this one we needed lengths to turn vectors because that derivative was a vector into numbers. This one we needed dot products to turn vectors into numbers. This one, well, we didn't need to do that. We just needed to turn it into, well, just in inverted commas, into two integrals. Okay. And now we get to 3D. Actually, before we move on, you don't remember seeing this thing, probably. No. Right, sorry. You probably don't remember explicitly being told about vector functions in 2D. But they are there because Green's theorem tells you how to connect these two. And I'll get to that when I get to Green's theorem. So, yes. Or do I do it now? Let's do it now. So let's just maybe have a look at that 2D vector function thing. This ds, which is a piece of the curve, ds there, that ds there is a vector. It's made out of a little change in x and a little change in y, which I haven't mentioned so far. ds is a vector. It's made of a little change. There's the curve. There's my ds. And it's made of a little change in x and a little change in y. Like that. So, when I do f dot ds, well, that's a vector as well, right? There'll be some function of x and y to produce the first coordinate, and some function of x and y to produce the second coordinate. That's how a vector function works. It produces two coordinates. I'm going to call them u and v. Or is it? Oh, no, I'm going to call them p and q. So, when I integrate the curve, that becomes, damn it, David. Where is it? There it is. I'm just getting ahead of myself. This fx dot ds becomes p of x, q of x dot dx dy. And when I do a dot product, I'll get this times this, and this times this, which means that what I'm integrating is this. There, wrong bolded. Putting a bold on the wrong one. And that is exactly the kind of thing that you integrate when you do Green's theorem. Green's theorem has a dx and a dy over here. If I've got it right, I'm going to have to look it up. Probably be quicker in your lecture notes, but I don't have a copy with me. 522. There it is. I've got a thing along the curve of f1 dx, f2 dy. That's what this textbook calls it. I've called that p and q. And so when you see Green's theorem, it's actually talking about half of Green's theorem is an integral around across a region. Half of Green's theorem is an integral around a curve of a vector function. But we've sort of skipped all the vector bit to write it in this format because this was before people thought about it as a vector function, when Green's theorem was invented. Okay. So, what Green's theorem does is it says it connects together these things. It connects together a vector function around a curve and a scalar function across a region. And it says as long as the function here is related to the function here in just the right way, then they will be equal to each other. Okay. So let me just see. What does my book say? My book says that the scalar function that I integrate has to be this. If the scalar function is this derivative, this combination of derivatives of the two pieces of my vector function, then the integral of this thing across the region is the same as the integral of this thing around the curve. So let's see if I can make that work. So Green's theorem says that the integral across a region of some function dx dy is the same as the integral around the boundary of the region. Is that how your lecturer writes it? Okay. And this thing here has to be dq on dx minus dp on dy. And just to remember, this is the same as the vector function pq dot ds. This is the same thing here, because the ds is dx dy. Okay. Cool. So this is Green's theorem. It connects a 2D vector function across a curve to a 2D scalar function on a region. Connects these two integrals together, but only if this function is a derivative of this function. And it has to be exactly the right derivative. So a different way of saying it is to say damn it, I need to put an X in there, sorry. Is that right? Yeah. I.e. a derivative of f, of big F. So that's one way of doing it. So we can say the f1 is the first coordinate of big F and f2 is the second coordinate of big F. So Green's theorem is extremely similar to the fundamental theorem of calculus. The fundamental theorem of calculus says that the integral of little f is the same as some other thing involving big F, but only if little f is the derivative of big F. And this says a double integral of little f is the same as a single integral of big F, but only if little f is a derivative of big F. It's just that it has to be the right kind of derivative for it to work. There's only one kind of derivative in one dimension, but in two dimensions things get a bit curlier. Literally. So this is the secret zero integral of not integrating. So we've got one integral here and no integrals here. We have two integrals here and one integral here. It's a bit like an integral cancels out a derivative. One of these integrals cancels out the derivative that's here. Right. Cool. That's why this section of the course is called the fundamental theorems of multivariable calculus. This is one of them. All right. So Green's theorem lives on my table. Here. So I'm just going to make that clear. These two are connected via Green's theorem. Okay. Because I wanted to use the Plato at least once, and this is good enough. I may use it again. Right. Okay, this connection is Green's theorem. Right. Beautiful. Doing well. In fact, just for future reference, let's do a diagram here that matches this picture. It connects these two on the 2D picture. Okay, let's do 3D. Yay. So what did I do in 2D? I did scalar functions first. So let's do that. Scalar functions first, then I started down with curves. So let's do the same thing. So scalar function across a curve. So now we're in 3D. And I have a curve doing whatever it does in 3D. And it still has a parameterization, the same as all curves have. And what this t does is it tells me where I'm up to on the curve. Okay. So, as the t moves forward a little bit, that will cause the curve, the point on the curve, to move a little bit. And it's exactly the same as it is in 2D. It's just that everything's got 3 coordinates. And so I can say that a little change in the position along the curve is the same as that. And so therefore, a little change in distance along the curve is the length of this. Just beware, this is a vector and that's a number. It's not traditional to put a number next to a vector in that order when you do vector multiplying by scalar, but we're allowed to do it if we want. And so the integral of the function ds, because that's a number, so I have to multiply it by a number to keep it as a number, is going to be, as t goes from a to b, of f of x of t, length of x dash t dt. All right, exactly the same as it is in 2D, except my curve is not necessarily, well, it might be in space. Just watching people's hands, so see if I can switch to the floor. And the red box was very clever of me, so that I know what the camera can be pointing at. So maybe my curve is in space, doing whatever it does. Or, you know, maybe it's a spiral. You know. Sorry? Yeah. Parameterize my leg. Yeah, I'll parameterize your leg. So maybe it's a spiral, and there's a number that tells me where I'm up to on this curve. And every point in space, including the points on my leg, have a number attached to them, and I'm going to add up those numbers as I go. Right, beautiful. Okay. So, that's how it works, and it's exactly the same as everything else. It's just that the vectors involved, the vector which tells you which direction you're moving is a 3D vector. And this and this length will be a 3D length. It'll be the square root of an x and a y and a z coordinate. And all of those will involve t's, and so you'll get some funky formula involving t, and you'll have to add it all up. Okay. What next? We're still in 3D, and f of x is going to be still a real number. It's going to be a scalar function. And we're going to do it across a surface this time. Do not like drawing surfaces So that's not too bad. So I want to take every point on this surface and collect together all the numbers that are attached to those points and take into account how much space on the surface they take up, like how much space on the surface has those numbers, and I want to add them all up. So that means the only way I'm going to be able to do this is to have a way of keeping track of where I am on the surface. So I need a parameterization, because that's what a parameterization is for. That's what parameterization tells you, where you are on the surface. So I need a collection of numbers, two sets of numbers, traditionally u and v, and together those u and v locate a point on the curve, on the surface. Okay. Usually you'll see these interpreted as x and y coordinates, which is fine. It's just easier for me to think of them as two separate things. So I can choose to do that in many different ways. So I can, if I want to, choose my u and v to be the space coordinates x, y, and z if I want. But I don't have to. And if I'm very, very clever, I can avoid the problem I had in 2D, where the choice of x changed which y's I was allowed to choose. So back in 2D, when I was doing this, depending on which x I choose, that changes how many options there are for y, because each of them is a different width. But if I'm very clever, I might be able to arrange my parameterization so there's always the same choices for v no matter which u I pick, and vice versa, if I'm very clever. And that is the cleverness of choosing a good parameterization. You want the variables to be independent of each other if you can. Let me just talk about that. There's a surface. Lives in the Maths Learning Centre most of the time. This is a hyperboloid of one sheet. I might just turn it up a different way so it's easier to see. There we go. It's a hyperboloid of one sheet. It has a nice saddle there. It's a good saddle point. It's sort of flattish at these edges and more curvy in the middle. And it has an equation something like, depending on where the x-axis is, it would be much nicer if my, it would be much nicer if, damn it. Much nicer if my x-axis was, damn it, I can do it, was in there, right down the middle of it. That would be much easier to deal with. And my y-axis is going to go through there. And my z-axis is going to go up here. Yeah. Okay. So that's what I'm going to do. And with that, this function has an equation something like right. Something like this. You can do it. That's what this function is. Minus x squared plus y squared plus z squared equals 1. Well, it's not a function at all, really. It's not a function because different x's and y's can produce multiple different z's. But it is the name of this surface. This surface is all of the points which satisfy that equation. Okay. So, if I want to parameterize it, I'm going to need a way of describing where I am on this surface, because at the moment this equation doesn't tell me where I am on the surface. It just allows me to pick a point, sub it into there, and if it comes out to 1, it's on the surface. If it doesn't come out to 1, it's not on the surface. So, well, these are circles this way. There, it's a circle. That's a circle. That's a circle. So I reckon I could choose which position on the x-axis I'm at first. And then once I've chosen where I am on the x-axis, I can trace out that circle somehow. I'm going to need the screen to do that. I did it again, didn't I? This is why this is one of the reasons we lose so many pencils in the Maths Learning Centre. I just leave them places. The other one is that people just take them like the spoons. It's very dark about the spoons. Okay, so let's just have an example of a parameterization. Just so you know, the reason I know it had the minus on the x is because that's where the axis was of my shape. The hole in my shape, if I put the x-axis along there, that one's different to the other two directions, and so its coefficient is different as well. If it was pointing upwards, the minus would have been on the z. Okay, let's see if I can draw a picture of this. I really should do it in colour. Something like that. What I'm going to do is I'm going to notice that it's mostly made of circles, so I'm going to choose x. And then once I've chosen x, I'm going to have to choose a radius for my circle. Yeah, that's interesting. Just a second. All right. Just rearranging that. That'll work. That's the radius there. You know, x squared plus y squared, normally in a plane it would be x squared plus y squared equals radius squared. But mine is in the yz direction, so it's y squared plus z squared equals radius squared. So the r is going to be root 1 plus x squared. Beautiful. And then I'm going to choose the position around the circle. And so that would mean that it has x-coordinate x, and the y-coordinate will be r cos theta, and the z-coordinate will be r sine theta, because you always choose a circle by doing cos theta sine theta, because it neatly finds every point on a circle. So what does that look like in total? So that r is actually this. So we actually end up with the x position is going to be x root 1 plus x squared cos theta root 1 plus x squared sine theta. And the x goes, well, in our case, the x goes for all possible x because I've parameterized the entire of the surface for the whole thing. But let's just do the one we've got, and maybe we'll say that this one goes from x equals 1 to x equals minus 1, hey? Doesn't really matter which end is which, really. So this would choose a position along here, and this will choose a position around the circle, and this root 1 plus x squared is the radius, which is based on the x that I'm up to. It's not as nice as I would like, but it is a perfectly good one. I'm sure there's more than one way of doing this. Okay. That secret of finding a circle, if you can create your surface as a stack of circles, it's the easiest way of doing a parameterization. Say, well, all I have to do is, if I have a stack of circles at different heights or different x's, then the height or the x is what tells you one part of the parameterization, and then how far around the circle is the other part of the parameterization. Okay. Cool. Anyway, that was a bit of a sideline of what we were doing here. What we were really doing here was attempting to find how to integrate across a surface. But to be fair, I suppose we should just be having a good look closer in at this. And going, well, there's a little teeny tiny bit of surface here, which does not look like currently it's in the same direction the surface is pointing. And that is created by sort of going du and dv. But that's not really du and dv at all. That's the du causes a change in this position that way, and the dv causes a change in this position that way. And so somehow one of them is one of those directions is some vector multiple of du, and the other direction is some vector multiple of dv. And we should multiply them together to get the surface area at that spot. So this little thing is called ds. That's a little piece of surface. And so the problem is it might not be a neat little rectangle. They might not be at right angles to each other. And so it might not be a rectangle, it might be a little parallelogram. And so I'm going to need to figure out how to do the area of a parallelogram based on vectors. All right. So one direction is going to be the derivative of the position I'm at as I move in u, and one direction is the derivative of the position I'm at as I move in v. So this direction might be xu du, and this direction might be xv dv. Okay. So ds is going to be the area created by the derivative of u of x with respect to u times how far u moves, and the derivative of x with respect to v times how far v moves, and the area created by two vectors is the length of their cross product. Yes. And du and dv are just numbers because they exist over here. And so ds is going to be that. I can bring them outside of the cross product. Cool. And so therefore, the integral of f of x ds across the surface is the same as the integral as u goes from wherever it goes to and v goes from wherever it goes to of fx, which is a function of u and v times xu cross xv du dv. Okay. Cool. I can now add up all those advent calendar numbers across the entire surface as long as I have a parameterization. Cool. So different parameterizations will produce a different answer for this, but they will also produce a different function of u and v when I sub u and v into here. Sub in u and v into there. And they will also have different limits. And so even though all of those things are different, if you use a different parameterization, the numerical answer at the end will come out to be the same thing. Because different parameterizations will move across this surface at different speeds, and this is how we're taking into account the speed at which you're moving across the surface. Okay. So far, just people still writing. So far, we've done a scalar function across a curve in 3D, and that was the same as doing a scalar function across a curve in 2D. They're the same thing, really. There's just the vectors have different numbers of coordinates. And now we've done a scalar function across a surface in 3D, and that was that's this thing, and it's very similar to the scalar function across a region area in 2D, except we had to use the rate of change of the parameterization here in order to create our little piece of area. Whereas over here in 2D, our little piece of area was just there. It was dx dy. And that's similar to the relationship here. We had to create our rate of change with respect to t using a derivative, whereas we didn't have to do that here over in one dimension. We can do it. We can do substitution here. So technically, substitution is a parameterization of the real line. Okay, so that's where we're up to. Cool. Now, where are we going to go from here? We're going to, well, there's another kind of object in 3D. In 3D, I can make 3D regions. I can make volumes. So we're going to have to do that. Oop, might just pop this under here. Okay. So I can do a scalar function across a volume. All right. Now, volumes are not nearly so nice on my space graph because they're harder to draw. Should have brought a balloon. That would have been so cool. So before, we were creating just the surface of this, just the red bit, the bit that's created by these lines here. This is a very special kind of surface. Most surfaces don't have lines in them. Like this one here, for example, doesn't have lines in it. It's very curved. No, it doesn't like the yellow side, does it? So that surface doesn't contain lines, but this one's very special. It does. My PhD had these in them. It's very, very fun. Anyway, I might not be interested in the surface. I might be interested in the space that it contains, the volume inside it, in there. Every one of the points in here also has a function value, because there's a function value at every point in space, everywhere. And so inside here, there's function values in there, and maybe I want to add up all the function values across the entire inside of this thing. Maybe that's what I want to do. And that's what I'm going to do. But this time, the amount of space that it takes up is a 3D space instead of a 2D space. So the classic at hand scale is to use Play-Doh. The outside of this is a surface. But if I was interested in adding up the function value at every point on the inside of this, that would be adding up inside the volume. So the boundary of this is a surface, the interior of it is a volume. And, all right, tricky. Actually, not that tricky. There's my volume. Okay. So it's very, very similar to doing areas in 2D, volumes in 3D. I need a way of describing where I am inside this surface, inside this volume. So I need to locate every point in the volume, and I will need 3 different variables to do this. Like that. So you might even use just the x-coordinate, the y-coordinate, and the z-coordinate, if you want. But you may also use completely different things. A classic way of making a parameterization of the space inside a surface, if you've already found the surface, is to add an extra coordinate. So this surface I had already found how to locate every point on the surface, on the edge, but I want to get to on the boundary, I want to get into the middle. Well, that's okay, because maybe this is like 100% of the way to the edge, and I could just have another parameter to say, well, what percentage of the way to the edge of this circle am I? So I could do the parameterization of, can I fit all of this at once? Parameterization of the whole interior volume of my hyperboloid. Minus x squared plus y squared plus z squared equals 1 for x between minus 1 and 1. Well, we had this. Well, we could just so this is the boundary. This is the very edge of my parameterization. And instead of given a radius, choosing the very edge, maybe I'll only go like 50% of the way, or 30% of the way, or 70% of the way, and that would fill out all of the spaces in between. And so I can do this. This was parameterization of the surface. Well, let's do this. So this was the x went from minus 1 to 1, and the theta went from 0 to 2 pi. Well, this is going to make, the p is going to go from 0 to 1, because it's like the percentage of distance to the edge. And that'll neatly cover the entire inside. Because at every radius I'll go, well, I'm only going to go 70% of the edge, and that'll be that bit, and I can cover all those percentages. It's a very clever way of creating the inside of something. And neatly, all those percentages are covered at every possible x and every possible angle, and so the p is independent of the other ones, which is nice. I'll put this back. Okay, but sometimes you don't need to do any of that. So I just need to point something out. When I'm doing this, I'm almost always not finding the volume of this shape. The shape itself is called a volume, but the thing I am finding is what I get when I add up all of the function values at all of the points inside this volume. The answer I have isn't a volume. It's the sum of something. It could be a mass, it could be a pressure, it could be a force, it could be a volume, but it's mostly not a volume that I'm calculating. So what I'm going to do is I'm going to do a triple integral across this volume of my scalar function and this little dv is a little box. And it's like dx wide this way and dy wide this way and dz wide this way. And dv is that little box. dx, dy, dz. And so what you'd normally do is you'd go, okay, my first coordinate will go between two things, my second coordinate will go between two things, my third coordinate will go between two things, and then I'll have f of x, and that x is going to be a function of u and v and w. Whoa. Ah, crap, David. So, if I had used x, y, and z, then it would have been this. So if I had chosen the x and then used that x to choose the y's and then used that x and that y to choose the z, this is what it would have been. But if I had to use a parameterization, then it would have been like u goes from somewhere to somewhere, v goes from somewhere to somewhere, w goes from somewhere to somewhere, f of x with the u, v and w subbed in, and there will be a thing here to describe how the three changes of dw, dv, du are related to the three changes of dx, dy, dz. So this thing will be, I believe it's called x, y, z, u, v, w. That thing. And that's the change of variables. Cool bananas. So if you do parameterize it using the coordinates you already have, you can just leave it like this. But if you use a different parameterization, you're going to have to take that into account. All right. Right. I'm feeling good. I don't know how you're feeling, but I'm fine. So I'm feeling good about doing all this stuff. So let's have a look at where we are. We've got a scalar function, and we've managed to add it up across a curve and across a surface and across a volume. And all three of those have required us to locate every point on the object that we're trying to do the integral of. Okay? And if you have a three-dimensional object and you want the entire space inside it, you need three parameters to tell you where you are. For a two-dimensional object like a surface, you need two parameters to tell you where you are. And for a one-dimensional object like a curve, you need one parameter to tell you where you are. Okay. And let's just see what happened here. I had to keep track of how changes in t caused changes in the position on the curve by using a derivative. In this one, I had to keep track of how changes in the u and the v created little areas on the surface, and I had to use a cross product to do that because that turns two vectors into an area. And in this one, I had to keep track of how changes in u, v and w changed a volume, and to do that I had to do a change of variables-y thing. And that happened over here in 2D. I didn't need this thing in 2D because I was in 2D. So presumably in 4D, if that was a thing, this one would start to need some sort of funky 3D cross-product thing. Yeah, okay. Sweet. We're doing very well. there's 2 more integrals to go. What if instead of every point having a number attached to it, every point has a vector attached to it? Every point in space, if I open the little advent calendar window, it gives me a vector, and that vector is pointing somewhere. And most people talk about forces like that. If I was standing somewhere and then put a little object in space, it would feel a force. Mainly with gravity, they would all just go down and they'd all feel a force. But the closer they are to the Earth, technically a greater force they will feel. And so we think about forces, whereas most people think about vector scalar functions as things like density or pressure or temperature. And I like to think about them as feelings. You know, how does the point feel? Maybe it feels hot or cold, that's temperature. Maybe it feels like it ought to go that way, that's a vector. Okay, so we're going to have a vector function. All right, and what we're going to do is we're going to go across a curve or a path. So this is the same as it was in 2D. Every point in space has a vector attached to it, but in particular the points on my curve have vectors attached to them. And some of those vectors are pointing the same way the curve is going, and some of those vectors not so much. So when I zoom in on a point like this, the vector goes this way. The curve is currently going this way. And so that's my ds there. And this orange bit is the component of the vector. This is f of x. This orange bit is the component of the vector in the direction of ds. And so I can do an integral. I can go, well, the integral, damn it, and there's also a parameterization, which tells you where you are on the curve. So the integral across the curve of f of x dot ds, it has to be a dot because I can't integrate a vector. I can only integrate a number, so I have to turn my vector into a number. The t goes from a to b of f of x dot x dash t dt. So the idea being that the ds, as t moves, the position moves, and so the only way to connect those is to do it via a derivative. Okay. That's the same as it was in 2D. It's just that all my vectors have 3 coordinates now. So my dot product involves more stuff. Beautiful. I'll pop that in the appropriate spot on my table. And there's one integral left. So I have a vector function, and I'm going to do it across a surface. How the hell am I going to do that? All right. Well, okay, every point in space has a vector attached to it, including the points on my surface. And somehow I have to turn those vectors into numbers because I can only integrate the numbers at every point on my surface. And with the curve, I had a parameterization that produced points on my surface. And when the u and the v moved, that causes this point to move, but every possible direction it could go, oh crap. I need one number to describe how this is related to the way that these are moving. And the solution to that is to find out not the proportion of this that's in the same direction as the surface, because the surface has multiple directions. There's only one direction that's perpendicular to the surface. So I'm going to find the proportion that's perpendicular to the surface instead. So when I zoom in onto here, and my surface is coming past here, and my xu du is this vector, and my xv dv is this vector, I would like to know what proportion of my field, of my function output vector is perpendicular to this surface. There. Now, this is something I'm going to have to look up the notation for. S is this is where I'm not sure how your lecturer does it. Does your lecturer use like an n thing at that spot? Yeah. So I'm going to have to dot it with a vector that's perpendicular to the surface so I can figure out how much is it in the direction of the surface. Something like that. Yeah? Okay. Sorry? Ah. Well, that's an interesting thing. I'm going to put this here. So this is really interesting. And there's a little Swiftie that we're going to pull here. We're going to go, well, when we looked at this, the area of this was the length of the cross product of these vectors. But the actual cross product of these vectors will be a vector that's perpendicular to this plane. And it will be the area long. And so it turns out that a vector that's perpendicular to this plane, which is the area long, will be the actual cross product. So this, we're going to say that this n hat dot ds is going to be called ds. It's a vector version of this little piece of plane. And that's what it means. And it literally means that. And so we get that this is u goes from wherever it goes, v goes wherever it goes, fx, and the x has the u and the v subbed in. du dv. Right. Ooh. Oh, it's actually inside the table. There's a little gap just here. Wow. Which is locked. Okay. Well, it's a bit of archaeology for the future. That's the most extreme loss of pencil I've ever done. Okay. So these are all our integrals. Here they all are. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So there are some theorems. There are some theorems that connect these integrals together. So we already had a theorem here, which is Green's theorem, which connected these two. So we want another. I should have drawn this on yellow. That would have been cool. I don't have yellow. I'm sorry. So Green's theorem connected an integral across a path of a vector to an integral across a region of a scalar. So presumably we should be able to do the same thing. And the answer is yes, we can. There is a connection here. It's Stokes' theorem. No, that's here. No, that's right. I could be wrong. Just going to check. Stokes' theorem says that we have a vector function, because it's in bold, across a curve, and a scalar function. Yep, gotcha. No. That's not Stokes' theorem. Stokes' theorem is this. Well, that's bizarre. It's not quite the same. Actually, it's this, isn't it? That's Stokes'... Oh, crap, just a second. That's Stokes' theorem. Well, I suppose we didn't have something in this position in 2D. So the 2D version of Stokes' theorem has to go over here. That's Stokes' theorem there. Stokes' theorem connects a vector function across a surface with a different vector function across a curve, as long as the curve is the boundary of the surface. Let's actually pop that in. So Stokes' theorem does a double integral across a surface. I'll put a bold in a second, I think. And a single integral across the boundary of that surface, which is a curve. Oh, capital S's and small s's, great. So this thing should be a derivative of that one in order to cancel out one of the integrals. And so this should be one of the derivatives of this. Okay, I think it's this. Crap, other way around. No, that doesn't. Yes, because the derivative has to go where the integral is to cancel out the integral. Damn it, David. Yes, that's it. This one has to be a derivative to cancel out one of the integrals. Right. That's Stokes' theorem. So the idea is that it connects integral across a surface of vector function is integral across boundary of surface of other vector function only when f is this derivative of big F. So that's a different way of thinking about it. That's Stokes' theorem. So Stokes' theorem goes in this position just here. Connects those two. Not quite enough space, but that's okay. I can't zoom out, but it's all right. The shape is fine. There's just enough space to see that this says Stokes. Okay. So there is another theorem that connects things together. So presumably this one connects a double integral and a single integral. There ought to be one that connects triple integrals and double integrals. So this is going to have to be the derivative of something. The only triple integral we know how to do is a scalar. We need a derivative of some function that produces a scalar. And the divergent produces a scalar. And so it would have to be the divergence of a vector function, so it's these two that are connected through Gauss's divergence theorem. Okay. I'm going to do it in the, oh crap, just a second. I'll do my two versions like I normally do. So you're going to have the integral across a volume of a scalar function is the same as a different integral across the boundary of the volume of a different vector function, as long as f is the divergence of big F. Yeah. All right, just let me check. D is for divergence. Theorem of Gauss 545. Yep, cool, I was right. Whew. So that theorem lives in my diagram over here. There. Those two are connected via Gauss's divergence theorem. So there's three theorems involving integrals and how they're connected. So here we go. So let me add these to the pictures. There is actually one more theorem that is similar to this. And it connects this to this. So there's one more theorem that allows, and it works here too, but that's weird there, so we'll do this one. There's one more theorem that connects this to this subtraction, and it says that if this function here, no, it connects this to there. There's one more derivative that we haven't done. We've done del cross f, and we've done del dot f. What about just del f? We haven't done the gradient. So it turns out that if this function is the gradient of a scalar function, then I can skip straight to here. So there's one more theorem. And your lecturer, well, the book that your lecturer was working on called it the fundamental theorem of calculus for curves. So the integral across a curve of vector function ds is f of, I just need my curve, I just need to draw my curve to make this make sense. My curve goes from the point A to the point B. So, integral across a curve of a vector function is f of A of B minus f of A when little f is the gradient of big F. So if your vector function is the gradient of a scalar function, then when you integrate it across a curve, you can just sub in the two endpoints of the curve into the scalar function and subtract them. Same as you do when you do one-dimensional calculus. So this one doesn't really have anything to connect to. It doesn't connect together two different kinds of integrals. It connects together an integral with not doing an integral at all, just subtracting. No, it's there. So I really like how there's this path that comes around here, that everything's sort of connected. So if I was extremely lucky, I could track my way down all the way to here if I really wanted. If I was very lucky. But I have a feeling that that would be really hard, because the only way to get from here to here is if that function is the divergence of this function. And the only way to get from here to here is if this function is the curl of this function. So that means that to get from here to here, we need that function to be the divergence of the curl of a function. And I'm pretty sure there's a theorem that says the divergence of a curl is 0. Is that right? So the only way to pass from here to here through these functions is for that function to be the 0 function, and the answer is 0. Which is pretty cool, I reckon. Yeah. And in fact, that's really nice that came up just then. I did not plan that. That it's really nice to see how that these are connected, and to wonder how to get from here to here, and to wonder what kinds of functions would allow you to do that. And the only functions that do are the 0 function, which is pretty cool. Okay. They are all of the integrals, and they are all of the theorems. I hope that was helpful. So, from this point forward, I could do some examples, if you like. Okay. And I know that it's like 12 o'clock, but the recording is going to go for another half an hour, so I thought I could just fill it up with examples. And then after that, there's the drop-in centre, and we can do, there's not very many exams left, so we can have an MCC zone if you want. Okay. I have to say thank you. I'm super proud of this. I love my diagram. I just wish it was better colour-coded, but because last year's MCC students, we did this in the Maths Learning Centre, and I wanted to do it on video so that future students could see it. Okay, so let's do some examples. So is there a curly one that you're that worried you that you've seen? Or am I going to have to make one up? Okay. Okay. Sure. Yeah. Okay, I'm just going to go to Kreisig. This is an old version of Kreisig, but it's still good. And there's an exercise here for using the divergence theorem. So let me do that. Right, this is my vector function. Where S is the surface described by x squared plus y squared is equal to a squared, and z is less than or equal to h. Well, the absolute, sorry, other way around, I put it in the wrong spot. The absolute value of z is less than or equal to h. Okay? So this is a vector function integrated across a surface. So in 3D we have scalar functions integrated across curves, scalar functions integrated across surfaces, and scalar functions integrated across volumes. And we have vector functions integrated across curves, and vector functions integrated across surfaces. And this is the one that we have. And so that's connected this way, but only if my f is the derivative of something. So if I could think of a function whose gradient was that, then I'd be good. But it's also connected this way by the divergence theorem. Yeah. Okay, so the divergence says that if I find the divergence of this function and integrate that across the interior of the surface, the volume, I should get the same answer as this. Okay? So let's see. So we know by Gauss's divergence theorem that the double integral of S of f dot ds is the triple integral across V of the divergence of f dV, where V is in the interior of the surface S. That's what we know. So instead of calculating the thing that we're going to do, we're going to calculate it using the divergence theorem. So first, let's do that divergence, eh? So we differentiate each of them with respect to the coordinate that they're in and add them up. That's how you do divergence. Okay, so d e to the x on dx plus d minus y e to the z on dy plus d3z on dz. That's the divergence. So we get e to the x. The z counts as a constant, so that'll still be there. And the derivative of minus y is just minus 1. And the derivative of 3z respect to z is 3. Okay, that's the divergence. And we're going to need to figure out how to locate every point inside this volume. So we really need to figure out what this volume is. So let's see. So x squared plus y squared equals a squared would normally be a circle in 2D. But since this doesn't tell me what the z coordinate is, it doesn't matter what the z coordinate is. So it will be a circle at every z. So I'm thinking that there is a circle of radius a at every z. That makes it a cylinder. So we have radius a, and this looks like the height upwards here is h and the height downwards here is also h. Because it says the absolute value of z is less than or equal to h, that means that z is between plus and minus h. Okay, so it's a cylinder. And we need to locate every point in the interior of that cylinder. So I could choose a z coordinate and then choose the circle and then go like p% of the way in. That sounds like a not too bad way of doing it. I'm sure there are other ways. How do you do cylindrical coordinates? Like a radius. Yeah, we could do that too. So, right, is cylindrical coordinates a thing in this course? Okay, so we could choose, the other way is to choose a height and then a radius and then go around the circle of that radius. So let's just draw that. We're first going to choose a height, then we'll choose a radius, and then we'll choose a circle of that radius inside here, and that's going to be our way of doing it. Okay. So we have that we choose a z, then we choose an r, and we choose the circle of that radius. And the z goes from plus h to minus h. And the r goes from 0 to a. And the theta would go from, damn it, I probably should put like, goes from 0 to 2 pi, something like that. It doesn't really matter if we have double counting at the edges, because when you do an integral, you're just doing the space on the inside anyway, so it's all right. Okay. Sweet. So we need to do the triple integral across this parameterization of that, and we're not going to be able to do that until we convert our dz dr d theta into dx dy dz. So we're going to have to do that. So let's see. dz on dx is 0, dz on dy is 0, dz on dz is 1, dr on dx. Sorry, crap. Damn, wrong way around. This is telling us what x and y and z are in terms of z and r and theta. So I need to do dx on dz is 0, dx on dr is cos theta, dx on... Just a second. Your lecturer allows you to skip to the end of this, don't you, when you've got cylindrical coordinates? There's like just a final answer that this works out to be. What is that answer? Okay, we'll just have to figure it out. dy on dz is 0, dy on dr is sine theta, dy on d theta is r cos theta, dz on dz is 1, dz on dr is 0, dz on d theta is also 0. Okay, so this matrix, the absolute value of the determinant of that matrix is what we need. So let's see, if I expand this matrix around this top first column, plus minus plus, I'll get the determinant of this bit here. So I get cos theta times r cos theta minus sine theta times minus r sine theta. Oh, cool, cos squared plus sine squared is 1. So I've got just r. Convenient. Okay. Cool. Don't like my chances of integrating this, but anyway, I'm just powering through. So, the double integral across my surface of f dot ds is the same as the triple integral across my volume of del dot f dv, which is oh crap, what's x? R cos theta. And z is just z. I don't want to integrate that. That's, what the hell is that? What are you doing to me? And I probably even picked one that there isn't an answer in the back. Oh no, it's an odd one, so we can see. I couldn't do that in the exam, of course. So maybe I should have chosen my coordinates differently so that my x didn't turn out to have something else in it. Yeah. Do not like it, Sam, I am. Well, I guess I could wait. No, it's all right. I really thought I had something, because if you know that all the positive ones cancel out with the negative ones, you can just sort of skip some of it. Sorry? I don't know. We probably didn't need to parameterize it. We could go back and not parameterize it. Well, my problem is, I can totally integrate these with respect to z, that's fine. And then I could integrate it with respect to r. But by the time I've gotten there, when I get to integrating with respect to theta, I'm going to have like a 1 on cos theta e to the r cos theta. And I don't like integrating that with respect to theta. Yeah?
Because they're all like numbers instead of functions, would like you be able to separate it into 3 separate integrals? Would that not work?
Well, I think I could separate it in, so you're saying do the integral of this and the integral of this and the integral of this. Yeah. But unfortunately I have to do the integral of this with all 3 of these. Yeah. All right. Well, we may come back to that. Let's see what happens if I don't parameterize it. Well, let's try a different parameterization. And just This is what I would do in an exam. I'd leave that like that and just try something else and see if I could come back to it later. So with this one, I really would like to leave my x as just an x. That would be useful. And if I could leave my z as just a z, that would be nice too. So if I could parameterize it in terms of x and z and then some third parameter, then that would be nice. So definitely I could choose a z. And then I could just choose an x between minus a and plus a, couldn't I? And then the y goes between like root something and root something else, I guess. So if I choose z for the height, choose x to be from minus a to a, and then choose y, and I'm going to need y squared plus x squared to be a squared. So the y is going to have to go somewhere between root a squared minus x squared and root minus root a squared minus x squared, and do that. So based on the choice of x, then there's different options for what y is for each one. Let's try that one. So it's not really a parameterization. I mean, it's still a parameterization, but it's just naturally figuring out what the coordinates actually are. Okay, so in that case, my integral across v of del dot f dv is just going to be the natural order, right? I'll choose my z, which goes from minus h to h. I'll choose my x, which goes from minus a to a. And then I'll choose my y to be from minus a squared minus x squared to plus a squared minus x squared. So what is this thing? Where is it? Oh, there it is. E to the x minus e to the z plus 3. dy dx dz. Well, now bloody hell there's going to be root a squareds minus x squareds in it. No. No. Yeah. So this doesn't involve a y at all, right? But the y does involve an x, so I can't bring this out. But it is a constant, isn't it? So it'll be constant times y. And the y goes from minus it's still bad. Trust me to choose a really bad one. So we're going to have this times that minus this times that, so there's going to be two of them. I don't want to integrate that. Have I missed something important, do you think, in the original function? Did I write the original function down correctly? I did write the original function down incorrectly. It's not a z, people. It's an x. Yeah, because I really don't feel like doing a trig substitution to do this. So it's an x. And in that case, when I do my gradient, this becomes an x. And they cancel out! Ah. Right. Which is just 3. Right. Right. 3 I can integrate. Oh. Rightio. And in that case, I don't even need to parameterize it. I can skip all of this. I can go back. This is just a second. None of this is necessary now, because don't need that, don't need that, don't need that, don't need that. Okay. Which is that, because we figured out what the divergence was, just the number 3. That's what we figured out. Which is 3 lots of this integral. And if you integrate the volume across the volume, the answer you get is the literal volume in like centimeters cubed. Because you're adding up all these little bits of volume across the volume, so you just make the volume, which is 3 times the... So I did need this. This is good. Okay. And so the volume of my cylinder, well, it had radius A and height 2h, and so the volume of my cylinder is 3 times pi a squared times 2h, which is 6 pi a squared h. Oh. Right. I did not feel like doing a trig substitution and it by parts, and I have a feeling that would just be horrifying and not turn into anything good. Okay, so that's why this example was chosen, because it came out to just be the volume of the thing. So if it turns out that you just get integral v dv, it's just the volume of the thing. And just like double integral surface ds, like small, not ds, like not bold ds, is the surface area of the thing. And if you happen to know that, then you can just do that. Right. Well, that turned out. So look at that. I went back and went, this is really hard, and so maybe I did something wrong earlier. No. And then I went all the way back and went, maybe I wrote the question down wrong. You can see that's good. David's exam technique. Should probably have written it down right to begin with. Right. Okay. That's totally an exam question. That question, where you have to notice that you get just the volume and say, oh, well, and that's just the volume. Yeah. Okay. Cool. Let me see if I can do a Stokes and get the question right this time. So we're going to find the closed path integral around the curve C of vector function f dot ds. Clockwise, as seen from the origin, for f being I don't know. Minus 3y, 3xz. And C is the circle x squared plus y squared equals 4, z equals 1. Okay. So we could just do that. We could literally parameterize that circle and do the thing we need to do. So we could do that. But this question says we have to use Stokes' theorem. Okay? And I mean, a classic assignment question is, well, you know, evaluate it directly and evaluate using Stokes' theorem. Check that they're the same answer. So, okay, so Stokes' theorem, curve surface volume for scalar functions and curve surface for vector functions, and Stokes' theorem connects these two. So we have a vector function around a curve, and we can turn that into a different vector function around a surface, and that to create a vector function from a vector function via a derivative, I would do the curl. So we know that. Okay. So I'm going to figure out the curl before I figure out what to do. Let me just check if I've written that down correctly. Minus 3y, 3x, and z. Okay. So let's see. Doing cross product, we're going to get d on dy of z, which is 0, minus d on dz of 3x, which is 0. And then we're going to get minus d on dx of z, which is 0, minus d on dz of 3y, which is also 0. And then we're going to get d on dx of 3x, which is 3, minus d on dy of 3y, which is of minus 3y, which is minus 3. And so we're getting 0, 0, 6. Okay. That's interesting. I reckon we're going to be able to avoid parameterizing this thing. So let's just actually draw this circle. The height is z equals 1, so it's in this plane where z is equal to 1. And as x squared plus y squared equals 4, which is a circle of radius 2. Okay. Right. And 0, 0, 6 is perpendicular to this surface, no matter where I am, because this surface is horizontal and 0, 0, 6 is vertical. So they said clockwise as seen from the origin, did they? So if I'm looking from below, well, clockwise from below is anti-clockwise from above. So that's this way. Yeah, because if you're on the other side of the clock, it goes the other way. Right. So that's good. Anticlockwise from above is nice because that's the correct direction for going around a circle if I'm going to use cos and sine. Okay, and so the normal vector I'm interested in is definitely pointing upwards. So this is interesting. So ds is n hat ds, right? Which is also like the parameterize-y thing with the cross product and stuff. But it's also this. Like this is what we had before. But we don't need that because I know what n hat is. It's 0, 0, 1 at every point on this surface because it's flat. So let's see. Where S is the interior of the circle. Okay. Is horizontal. And so that's of 6 ds. Oh, look at that. Which is the surface area of this thing, which is a circle of radius 2. Oh, the suspense is killing me, my pencil. Bang! All right, there we go. So it turns out that even though many of these integrals are not areas, sometimes they are. All right. So just to make sure we're doing this right, I just want to do this path integral directly, just in case. Now, if I was in an exam, I totally would not, because there's not enough time, but I just want to check. So that path integral directly, we're going to need a parameterization of the path. And so the the coordinate of something on the path is going to be like 2 cos theta, 2 sine theta, 1. So this bit makes the circle. Oh, did it say 4 squared? No, just 4. And this bit makes the z coordinate 1. Okay? So to do a path integral, my ds is my x dashed of the, well, I need my theta. Is x dash theta times d theta, which would be minus 2 sine theta, 2 cos theta, 0 d theta. And so the integral around C of f dot ds is, oh crap, just a second, almost there. I need to figure out what f is in terms of theta. Minus 3y, 3x, z, which is minus 6 sine theta, 6 cos theta, 1. So the integral around the curve of f dot ds is the integral of theta goes from 0 to 2 pi of minus 6 sine theta, 6 cos theta 1 dot minus 2 sine theta 2 cos theta 0 d theta. More paper. Which is the integral of theta goes from 0 to 2 pi of 12 sine theta squared plus 12 cos theta squared plus 0. Look at that. So 12, well, sine squared plus cos squared is 1, so we just get 12 d theta, which is 12 theta from 0 to 2 pi, which is 12 times 2 pi minus 0, which is 24 pi. Yes. Though I guess if it's like that, it should be in Spanish, and it should be sí. Okay, cool. I don't know if there are productive examples, but you can look at the other revision seminars for more complicated examples if you like, and we can talk about them till we're blue in the face until your exam comes. Thank you. Yeah.
Philosophical question about it.
Yep.
If you take an area integral,
Mm-hmm.
can you do it if the area intersects itself?
I think if you take an area integral and the area overlaps itself by a region, then you end up with whatever the region is, the integral of that just region by itself twice. But if it just intersects with just along a line, then so if you've got a region that intersects itself just along a line, that won't make a difference to the integral.
I mean, more like there's a curve which like goes up and around.
Yep.
And you take the area of that.
Yeah, well, it's a bit tricky. So you're asking a curve in space, or
2D, just like
something like that.
Can you do that?
Probably. But you have to be really careful of what counts as the inside. I don't really know the details of how you do that.
So if you just said that it was this,
Yeah,
I
think if you do Green's theorem around this curve, it will produce those 4 areas. Like when you're doing Green's theorem to find the area of something.
Yeah.
I think it will provide the area of those 4 pieces summed up. And I think if you do Green's theorem around this, it will be just that bit.
Yeah. Okay.
But I don't really know.
Yeah, that's about what I expected. Thank you.
Yeah.
That was really good, David.
Thank you.
One thing here, I'm not quite sure with divergence theorem. Because in the lecture note it says it has to be a closed surface.
Yeah.
Yeah, okay. Because we literally had the same question in the practice exam, when it was like, we have to prove that the divergence of the curl is 0.
Yeah.
Then it just was like Green's theorem, Stokes theorem, and divergence theorem, and why is it not good?
Right.
Yeah, and it was missing